Have you ever wondered why a rocket goes up even though gravity is pulling it down so strongly? Let's explain this using one simple force balance. Before just jumping into this topic directly, we would like to first develop some theoretical background for that. As we can see here, this rocket system is actually a variable mass system. And for this variable mass system, we would like to first develop some theoretical background. So let's discuss the motion of an object or a system of objects with variable mass. Let's say we are having an elementary mass dm, which is having an initial velocity u along this x direction, and also we are having another mass m, which is bigger than dm. That m mass also having an initial velocity along this x direction, that is v. And if this u is greater than v, then at certain point of time, these masses are just going to collide with each other. And if this collision is non-elastic, completely non-elastic, then these masses will just get stuck with each other and they will form a bigger mass, let's say dm plus m. And this combined mass will have a combined velocity. Let's say this is your v plus dv. So this situation is your before collision. Let's say at time t, and this situation is your after collision. Let's say at time t plus dt. So as Newton's second law states that the rate of change of momentum of a system is equal to the net external force applied to the system and the direction at which the net external force is applied, the change in momentum of that system will also occur along that same direction. So to find the rate of change of that moment, the rate of change of momentum of that system, let's find out the initial momentum of the system. Let's say that is your p vector, that is equal to u vector dm plus m v vector. So this is your system's initial momentum, and what will be the final momentum of the system, that is p plus dv vector, that is your dm plus m v vector plus dv vector. So that will be dm v vector plus dm dv vector plus mv vector m dv vector. Now notice one thing is that this dm dv vector is relatively so small in comparison to the rest of the terms on that right hand side. So we can just ignore this term because it is very 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 small in comparison to the rest of the terms on the right hand side. So this right hand side becomes simply mv plus m dv plus v dm. This. So it's the change in momentum of the system. That is your final momentum minus initial momentum, that is equals to v vector plus md v vector plus v vector dm. This is your final momentum, and the initial momentum will become this. So your mv will get cancelled out. This p vector will get cancelled out. So what we finally have is dp vector, that is equal to m dp vector minus of u minus v dm. Don't forget to put this vector signs here. So now if we divide this both sides with dt, that is the time between these two events, we will have this. Now notice one thing very carefully, that this dp vector divided by dt, that is your rate of change of linear momentum of the entire system. So according to Newton's second law of motion, that is your net external force applied to the system. So that will become simply your net external force. Now this dv by dt is your acceleration. So this term is your net force applied to the system, which is your f net minus of. Now notice one important thing here is that if we are having a particle 1 and particle 2, it is having a velocity u and it is having a velocity of v, and if we want to find the relative velocity of 1 with respect to 2, then what we do is simply velocity of 1 minus velocity of 2, that is your u minus v. So basically this u minus v is your relative velocity of mass dm with respect to this bigger mass m. So we can simply just write here relative velocity times dm by dt, that is rate of change of mass. So if we rearrange these terms with each other, we will have f net is equal to f external plus v relative divided by dm by dt. Now notice another important thing here is that this term is your force, this term also is your force. So this term has to be a force, has to represent a force, and we call this force thrust force. So we used simple dimensional analysis here. So f net is equal to f external plus f thrust force, and this is our final expression here. So now, as we are all well equipped with the theoretical background we need, let's move on to the previous example to discuss the rocket motion. So the equation we obtained here is that the net force is the summation of external force and the thrust force. And the expression for the thrust force, we have thrust force is equal to V relative times dm upon dt. And this V relative is the relative velocity of the exhaust gases with respect to the rocket. And this dm upon dt is the rate of change of mass of the rocket. So now let's say we are having here a rocket of mass m. So this gravitational force will act upon it along this downward direction. Let's say that is Fg vector, that is equals to mg vector. And what is also happening here is that when this rocket engine burns all its fuel, all the exhaust gases are ejected downward, let's say with velocity v relative vector. Now let's take this downward direction as negative and this upward direction as positive. So the expression for the thrust force we have here v relative vector times dm upon dt. So this relative velocity of the relative velocity of the exhaust gases with respect to the rocket is negative because it is along this downward direction, and this dm upon dt, which is the rate of change of mass of the rocket, that is also negative because it's decreasing. So this thrust force becomes positive. So positive means that this thrust force is actually getting applied on the rocket along this upward direction. So now the expression for the net force we have here, F net is equal to the external force, which is equal to the gravitational force Fg plus the thrust force, that is equals to, now we can write this equation as like that, minus of mg plus the thrust force. We took the minus sign because it's acting along this downward direction. From this equation, it is pretty evident that if this thrust force is bigger than mg gravitational force, then your net force will become positive. And positive means that it will act upon this rocket along this upward direction, and in that case your rocket will just lift off. So that's all. So a rocket doesn't rise because it's fast or light. It rises because it throws mass downward fast enough to beat gravity. That's the physics of rockets.